Greetings everyone! Today we're going to explore solving real-life applications using our logs and exponential functions. So what I love about logs and exponentials is this is a topic that is very true to life. It's something we can use in many different ways, so it's really easy to explain that true life application. So to start off, let's go back to what we already know. If we go back to basic exponentials, especially graphing, right? If I had something like 2 times 3 to the x, you could create the parent table with that base of 3, and you could create your y values. So 3 to the negative 2, 1/9, 1/3, 1, 3, 9, remember that? And then this stretched or compressed your y value. So we would take all of these times 2. Okay, remember that? So knowing that information and how these work, the b value was your factor and the a becomes your initial amount, because look at that value. You end up with 0, 2 as your starting point or your y-intercept. So if it's your y-intercept, we're going to think of it as your initial amount in the real world. All right, so let's take some notes on how this would apply directly to us in the real world. So to start off with a basic equation, the a value is going to stick to your original amount. That depends, if I have $500 in the bank to start, then my a value would be 500. If we're talking bacteria, maybe it's a huge amount and we're trying to decrease. And then very relatable right now, you guys, to the current situation here in 2020. So original amount, where's your starting point? Okay. R is going to be your rate or your percent. For example, if a certain virus is doubling every day, okay, versus if it's a half-life. Let's say if I just tell you it's increasing by 5%, all right, whatever that change number is your rate. But just remember, if I say 5%, you need to write it as 0.05. So don't forget that conversion, okay? Write it as a decimal. Your t is going to be the number of times it's applied. So are we talking weekly? How many weeks are in a year? Are we talking biannually? Are we talking quarterly? It's going to be presented time-wise in different ways. So keep an eye out for what that number means and represents. And then, of course, whatever it's equal to is your final value. Key thing, I think you need to memorize this. A times r to the t, because we're going to add one other element to it. Specifically, that element we are going to add is specific to growth or decay, meaning if I give you an initial amount, you want to keep 100% of that initial amount. So if I'm talking a bank account with interest, let's say I deposit $100 and then I'm earning a rate of 3%. Okay, I don't want just what the 3% is. I want 100% of my money, and I want to add on 3% after whatever time that is. Okay, so the 1 represents 100% of the a value. Same thing with decreasing. If we're talking decay or decline, we're starting at 100% of that value and we're slowly getting rid of, let's say, 3% of whatever it is. So that 1 is going to be very important. 1 plus or 1 minus. Is it growth or is it decay? Again, I recommend you memorize this. So to be honest, I'd memorize one of these and then just remember you might have to change the sign. So let's jump into some examples. In this example, you've purchased a new boat in July of 11 for $50,000. The boat depreciates by 12% of its value each year. Very common, right? They always say the second you drive something off the lot, you've lost value. So key words we are looking for here. Whoops, sorry about that. To start off with, we've got $50,000. That sounds like an initial amount. Okay. And then we see this word depreciates, going down. That's talking about a negative change. We have our rate of 12%. So let's start just setting up an equation here. I'm seeing y equals an initial amount of 50,000. It's depreciating a 1 minus 0.12. And each year, I guess it would depend on what time value is given to you. All right. So let's start off with question A. Question A says the value, let's find the value of the boat to the nearest $100 in July of 2020. So I'm going to use my equation. Initial amount, 100% of that depreciated by 12% per year. If I bought it in 2011 and now it's 2020, that's 9 years that we're looking at. Make sure if you are using, depending on what kind of calculator you're using, parentheses, very important. It says round to the nearest $100. So rounding is important. So in my calculator, I'm going to do 1 minus 0.12 equals. And then I'm going to take that to the 9th power. And then I'm going to times that by 50,000. So if you're not using a scientific calculator, you'll want to kind of work in to out. So if we round to the nearest $100, I have $15,800. Make sure you label and round correctly. During what year will the boat be worth 20,000? So now I know it's worth, I still know its initial amount. I still know its depreciation rate, and now I want to find its time. So in this case, I know it's going to be earlier than 2020 based on the previous question. So we need to do order of operations backwards. So first I'm going to divide both sides by 50,000. Well, let's narrow that down. Cut out a 0, cut out a 0, cut out a 0, cut out a 0. 2/5, make your life easier. Don't use a calculator. Minus 1.12. Well, wait, let's take care of that. All right, 1 minus 1 point. Wow, 0.12. Sorry, I can't say that. So we've got our 0.88 to the t power. So here's where we need what we've been learning, okay? I don't know that exponent. I need to use logs. So the base becomes the base. The answer becomes the exponent. That's handy. And the answer becomes the main value. All right, so here's where we have to go back to using our log-based function on our graphing calculator. Okay, so I'm going to leave this open to you. I don't have my graphing calculator in front of me, to be totally honest. But we know we're looking for what year. It's not going to be 2020, it's going to be before then. So don't tell me 4 years, okay? Tell me the year. All right. But again, you need that graphing calculator. Go to math and go down to log base and use that function. All right, let's take a look at some investments. Okay, very similar to exponential growth. It's just going to be some different vocabulary you're going to hear. So for example, P is going to stand for principal amount. Instead of saying original or initial, in banking we say principal. All right. We're still going to have an interest rate. Obviously, it's a bank. We're going to have that interest rate. We're still going to have time in number of years as the exponent. But what's different, what we have to watch out for here, is if it's compounded, then we're going to have this n value that we have to use. Okay, so if I say compounded quarterly, then I'm going to have to apply a 4. If I say compounded biannually, I'm going to use a 2. Monthly, I'm going to use a 12. So again, you need that word compounded if you're going to use this equation with the n value. All right, so keep an eye out for that. Be very careful, be very careful with the vocabulary. The last equation that we're going to jot down on this slide is compounded continuously. We're not going to work with this one very much, but occasionally there are bank accounts that are compounded continuously. And to deal with that, that's where the base E actually comes in. Okay, you have an E button in your calculator. It creates an exponent. We can use a rate and a time and a principal, but that's a very unique situation. All right, let's take a look at an example that deals with that growth and decay specific to money, investments, and compounded. So first of all, in this scenario, we're looking at investing $3,000 into a bank that pays 4% interest, but the key word here is compounded monthly. So compounded, I'm going to deal with that end value, and monthly means it's going to be 12. That's what we're looking at here. So to start off with, first question, how much money will you have in 6 years? So basic equation. I'm looking at a principal initial amount. You can still think initial, okay? We're just going to use the letter P in some of these. I'm going to keep all of it, and I'm increasing. Interest means I'm gaining money at a rate specific of 0.04. Compounded monthly, there's where my end value goes in the denominator and as the exponent. And my time is specifically 6 years. So I want 6 as the other part of my exponent. So if you are using a calculator that's not scientific or graphing, you're going to have to start from the inside out. So this is what I do in my calculator. I'll just read through it. 0.04 divided by 12. Add the 1. Take that answer to the exponent of 12 times 6. What does that get me to? 72, so an exponent of 72, and then times it by the 3,000. All right, so I actually arrive at approximately, it's money, $3,812.23. Depending if you round it as you solved, the penny might be off a little bit. Okay, so I'm open to if you round up or down there. But pretty basic. But let's take a look at the other scenario. What if I know a goal? I'm saving up for a vehicle or something I want to buy. So let's say I want to save up to $5,000. And I only have $3,000 to invest right now. And the bank's telling me they'll give me a rate of 4% and they'll compound it monthly. And I want to know how much time until I arrive to that amount. All right. So first I'm going to divide both sides by 3,000. That simplifies that down with all those clean zeros, right? We've got 5/3. Let's look at the inside of the parentheses. If I divide and then add 1, it's going to be a crazy repetitive number. So write down as many values as you can, and then you're going to have to the 12t still. All right. Here's where I now have a purpose for using logs. If I look at my log, the base becomes the base. If you can keep that decimal in your calculator in memory, that would be the most exact value you could do. The answer becomes the main value, or you could say the exponent becomes the answer. That's how I always think of it. Base becomes the base, exponent becomes the answer, all right? So now this one actually has multiple steps. You have to use a graphing calculator here because you've got a unique base. So that left side, when you type that in, you get approximately or around 155.0509. So practice that in your calculator. Still equal to 12t, you guys. So we actually have one more step on this one. We have to divide by 12. And when we do that, we arrive at approximately 12.9 years. You could get specific with months. I'm not going to be picky about that. But this is a real scenario in the sense of if I need to save up for something, the bank's going to help me figure out how long it would take to save. So there we go, guys. Just some basics on how we can use logs to solve financial goals, growth and decay of any scenario we're given. So as always, make sure you check out Google Classroom. Make sure you check out PowerSchool. How are we doing? I'll probably contact some of you just to see where we're at grades-wise. And if this is the year 2020, this is your last new lesson. Yeah! Don't worry, you'll still hear from me after this video. But I hope you do well. I hope you're doing awesome. And if you need anything, let me know. And until next time, take care.